I'm honored to be asked to speak for this distinguished group this morning, and I'm excited to talk about a project which I believe could have some could bring about some fundamental changes in the way that we generate power from coal. So before I get into that, I want to take those of you who are engineers, I want to take you back to college and to Thermodynamics 101. And in your thermodynamics class, you probably remember learning about the Carnot efficiency. So Monsieur Carnot, a long time ago, postulated that the efficiency of a heat engine was a function of the ratio of the coldest temperature in the cycle divided by the hottest temperature in the cycle. If we have a power plant, we're pretty much limited on how low we can go by where you place the power plant. And if we put all the power plants in the Arctic, we could go lower than we have if we're in the US. So really the one lever that we have to get to higher efficiency is to go to higher TH, to get to higher cycle temperatures. And that's exactly what we did during the first 70 years of coal power in the United States. Still, my father was also a Dr. Phillips, and he was a professor of American history. And so in honor of him, I always try to put some history lessons in every one of my talks. So this is it. So here's Thomas Edison's first power plant had a 3% thermal efficiency, 3, all right? 70 years later, at the Eddystone plant in Philadelphia, we're way beyond that. And the fleet average is now at 33% in 1960. So a factor of an 11 improvement over that time. Steam temperatures ramped up from about 600 degrees Fahrenheit to between 1,000 and 1,100 during that time. But notice what's happened in the last 50 years. We've flatlined on efficiency. What happened? Why didn't it go up? Well, it turns out we ran into a fundamental limit in the strength of ferritic-based or iron-based steels. 1,100 degrees F. Go much beyond that, it starts to lose its strength and will not be able to hold the pressures of the steam. So if we want to go beyond this level, we are going to have to go beyond ferritic steels. Now luckily, there's been a long, sustained effort funded by the U.S. Department of Energy and the state of Ohio, which has set the stage to allow us to now go beyond iron-based steels. And so I'm going to talk a little bit about some of the highlights from this 14-year effort, which wrapped up last year, started in 2001 and ended last year. So on the boiler side of this effort, we were looking to develop materials which, as I said, could sustain steam pressure at temperatures up to 1,400 degrees F. And the culmination of that was this steam loop, which was installed at Alabama Power's plant Berry down near Mobile. And what we did was we took the steam at 1,000 degrees F from the power plant and sent it through this special superheating loop. And by the time it got to the end of that, it was at 1,400 degrees F. Now from there, we just de-superheated it and put it back in the cycle. But we were able to run this, and this is a coal-fired power plant, for 33 months, more than 16,000 hours. We then pulled the loop out, chopped it up, did all kinds of microscope inspections, and the evaluations are, it looked good. And this is just some of the data that's here, and the green triangles are from the plant Berry test, and you'll see that well, 760 degrees C is 1,400 degrees F. So you can see that we actually went beyond that. The metal got hotter since the steam on the inside was at 1,400 F. The metal on the outside was actually a little bit hotter than that. But you can see we're at like 1 mil per year. So that gives us the confidence that we have the materials now that can go into a coal power plant at these temperatures and last for 30 plus years. Now you also need to have a turbine that can take 1,400 degrees F. And so the program also had a steam turbine focus. General Electric was the lead technology supplier on this part of the project. And when you look at a turbine versus a boiler, what stands out are the thick metal pieces that you have to make. So that you have to make this rotor perhaps by forging it, which means is doing like a blacksmith does, heating the metal up till it's red hot and then squeezing it into the shape you need. And then you need the very thick outer casings of both the turbine as well as the control valves. And so those typically are done by casting, taking molten metal and pouring it into a form. And so we needed to prove that we could do those two things, among others. So one of the culminations of this project was a very large casting, which was the size of half of a full-size steam control valve. So we took half the body there and formed it with a casting. Here you can see the molten. This is Haynes 282 from Haynes International in Fort Wayne, Indiana. So they're pouring that into the casting. Here's what it looked like after it's been formed. We again chopped it all up. The materials specialist at Oak Ridge National Labs, among others, did all kinds of analysis. Don't ask me what an SDAS value is, but apparently that's very impressive. Okay? And so just to summarize this 14-year effort in one slide, I can say that we had unprecedented success in developing materials that will allow a steam cycle to operate at up to 1400 degrees F. Both laboratory data. We have samples that were held under pressure and stress for more than 50,000 hours at 1400 degrees F. All right, that's a long time. I can guarantee you that the P91 and P92 that are in power plants today never saw that kind of testing in the laboratory before they went out into the power plants. And then we've fabricated materials and shapes that you'll need for a power plant. We've done the field tests to show that the corrosion is acceptable. So these materials can be used in advanced supercritical cycles, and next slide I'll say something about the economics of that. They will also can be used in supercritical CO2 cycles. Armin Cohen just talked about net power cycle. They are the largest user to date of Inconel 740, which is the other nickel-based alloy that was confirmed by this project. And Inconel 740 is made by Special Metals in Huntington, West Virginia. It's the only place in the world where you can get it. And we also believe that this technology could be helpful in retrofitting existing plants to allow them to improve their efficiencies and lower their CO2 emissions. So economics, look at these two columns. So this one with PCC means post-combustion capture. So this is a coal power plant with 1100 degree F, main steam and reheat steam, post-combustion capture. And that is one with post-combustion capture, 1350 main steam, 1400 F reheat steam. And if you come down here and you look at the total plant cost, the other thing is that we're capturing CO2 emissions to get to 1,400 pounds of CO2 per megawatt hour, which is the new source performance standard for coal power plants. All right, so in order to do that with this technology, which is proven today, it's basically the power plant design that is in use at AEP's Turk power plant in Arkansas. You need to capture 24% of the CO2. And it's going to cost you $3,300 per kilowatt to build it, and it's almost $100 a megawatt hour levelized cost. If you go to the higher efficiency, you need to capture less CO2 because now you have a lower CO2 emission, uncontrolled, 1592. So you only have to capture 15% of the CO2. Consequently, the cost of the power plant on a dollars per kilowatt hour basis are less, and the cost of electricity is less. So there's at least a $5 per megawatt hour advantage for this technology. So now that sets up the next step. And now the Department of Energy and the state of Ohio have provided money to go forward with what we're calling ComTest, which is short for component test. We're going to be fabricating both boilers, components, and a turbine, about a 7 or 8 megawatt steam turbine, as well as full-size valves for that steam turbine, and we are going to operate it. So this is just a little diagram of the concept. Similar to what we did down in Alabama, we will be taking steam from a host plant and then have a fired superheater. Sorry, but it's going to use natural gas. That's going to get you up to 1400 degrees F. Now, this superheater is not just one little steam loop like we had in Alabama. It's going to be a full fired, almost looking like a boiler. So this is a substantial piece of apparatus. It's going to produce 130,000 pounds of steam an hour at 1400 degrees F. And we will take that into the steam turbine that General Electric is building and drive at this point, a water break is what we're anticipating. In addition to that, we're going to have a cycling header test, which will simulate the header that you would have in a boiler. And what we'll do there is we will alternate, we'll go through temperature cycles to simulate starting up, shutting down. And we'll do that by alternating, sending 1400 degree F steam and then the colder steam that comes from the host. So we'll just flip back and forth, back and forth, back and forth. Hope to get 20,000 cycles on that. So where we're going to do this, in the great state of Ohio, there is a former Ohio Edison power plant in downtown Youngstown that is now used for district heating only. It is coal-fired. And so we're going to get the steam from them and then superheat it, run it through the turbine, and we'll install all the equipment there. They have enough space. The schedule for this is shown here. We started late last year. We're now nearing the end of the feed stage. I have preliminary cost estimates for the project. By this time next year, we hope to be finished with all the detailed engineering and have approval to go into construction. And then we hope to have the first fire and start producing the superheated steam in September 2018. Run it for 2 years' time, and then have a little bit of time for assessment and final reporting.